Good evening, everyone. It's 6 minutes past 6 on this wonderful Saturday evening, and we are just one day away from the National Science Day. Today, amongst us to talk about chaos in biology, we have Professor Sarika Jalan. Professor Jalan works in the field of non-nuclear dynamics and complex systems. Her broad interests lie in the broad research of complex biological systems and networks, spectral graph theory, random matrix theory, synchronization, coupled chaotic dynamics on large networks, delayed networks, extreme events, adaptations, and evolution. Professor Jalan completed her PhD from the Physical Research Laboratory, Ahmedabad, followed by a postdoc at the Max Planck Institute of Mathematics in Sciences and Max Planck Institute of Physics of Complex Systems, Germany. Currently, she is at the post of full professor at the Indian Institute of Technology, IIT Indore. She is the editor-in-chief of the Journal of Computational Science and an elected executive member of the Complex Systems Society. She is also the editor of Chaos Solutions and Fractals and served as a visiting scientist at the IBS Center of Theoretical Physics, South Korea. We are really eager to hear from you, Professor Jalan. The stage is all yours.
Hi, Ashmita, and everyone. Thank you, Ashmita, for very nice introduction. So let me start sharing my screen, and then I'll proceed. So, today this talk I have worked hard to make it at very popular level. So I assume that in general people don't. So this talk is mainly for those who don't know anything about chaos. Okay. So forgive me, those people who are already have some courses in chaos, because I am not really going to tell something new for those who already know chaos. So this is mainly for the people who don't know chaos, and I have taken few examples of biological system because it is supposed to be chaos in biological system. And I tell you, it was really very nice experience for myself and all my lab people, because I was asking my lab people to supply me a lot of information about chaos in biological system, because I am from physics background. So let me start with that, and let me make it full screen. Play from start. Just 1 second. Full screen where I don't want to make just do full screen, arrange. Okay, maybe. Okay. So all of you can see my slides and can hear me. Ashmita, you can just tell me if you can. Okay. And in between, if you have any questions, please keep on writing in the chat box. Okay. And I will keep reviewing the questions. And I want it to more interactive. I don't have this intention of just giving the talk and go away. So if you have any doubt or any interesting things, just keep on writing down in the chat box, and I will keep on looking at and try to address those concerns. So my talk, I am going to start with this clip from Jurassic Park movie, which was also actually, this idea was given by the organizers themselves when they send the mail, and they have written about this Jurassic Park, where this Dr. Ian McCallum, played by this Jeff Goldblum, he was the mathematician and a specialization in chaos. So let us hear that what he's telling, and it's just 1.5 minutes slide, which just 1 second. Yes.
Now eventually you might have dinosaurs on your dinosaur core, right? Hello? Oh, hello? Yes?
I really hate that man.
See, the Tyrannosaur doesn't bring set patterns or park schedules, the essence of chaos.
Still not clear on chaos.
It simply deals with predictability in a complex system. The shorthand is the butterfly effect. The butterfly can flap its wings in Peking, and in Central Park you get rain instead of sunshine.
Why?
And then I go too fast. I did a flyby. So give me that big glass of water. We're going to conduct an experiment. It should be still. The car's bouncing up and down, but that's okay. It's just an example. Now, put your hand flat like a hieroglyphic. Now, let's say a drop of water falls in your hand. Which way is the drop going to roll off? Of which finger or over the thumb? Or
Thumb.
Okay.
Right.
Okay, now freeze your hand, freeze your hand. Don't move. I'm going to do the same thing. Start with the same place again. Which way is it going to roll off?
Let's say back. Same.
Same back. Why? Because tiny variations, the orientation of hairs and hands,
Yeah, look at this.
the amount of blood descending in the vessels, imperfections in the skin,
Imperfections in the skin.
and never repeat and vastly affect the outcome. That's
Unpredictability.
So that's it. So he was telling about this unpredictability. So he was putting the drop of water, and despite like this was very vague experiment, but despite of putting this drop of water at the same position, you cannot predict that which side the water will fall. So unpredictability, that is the essence of chaos. And here is a definition, which is very popular definition, which I will come in. I'll try to describe at least this definition, which is sensitivity to initial conditions. It means if you know exactly the position and momentum to the infinite decimal point for a particle, then we can determine the future very well. So it's a deterministic system. It means give me the coordinates of present and I will tell you the future very well. Exact. So it's a deterministic. It's not a random system. It's a deterministic dynamical system. So what makes it chaotic? That is, if you tell me approximate present, if you tell that, okay, particle position is not x0, it is just some x0 plus some epsilon. Can you tell me what would be the particle position after some time t? That I cannot tell. So it means it is unpredictable. So if you tell me approximate position, I cannot determine the approximate future, and that is chaos. So for regular system, if I know that x0 at time t, if at time t is equal to 0, the position is x0, then at time t plus 1, position would be xt plus 1. I know exactly. But if you tell me that x at time t is equal to 0, if it is x0 plus epsilon, for regular system, I should say, okay, the future position also should be in the vicinity of epsilon. But for chaotic system, it can be anywhere in the phase space, however small epsilon would be. So however small the initial error would be, irrespective of that, your final position can be there anywhere in the phase space. So it's an unpredictability which makes this kind of chaotic systems, which are very nice dynamical deterministic system, very interesting. And please just note it, they are not random. These systems are not random. They are very well defined by the law of motion, like dynamical equations which defines them. So determinism plus unpredictability, that is equal to chaos. So deterministic system, but we cannot predict, and that is chaos. So it dates back, actually, let me just give some pedagogical kind of brief introduction. So this chaos in dynamical system, it dates back to late 19th century, when this Henri Poincaré, this French mathematician, who asked a question that, like Newtonian mechanics was already very well trying to describe the position of massive particles, but he asked a different question. He asked whether our solar system is stable. Like, for example, when we have two body interaction, sun and moon is there, sun and earth is there in the picture, we can very well predict everything. But as soon as you put one more entity, which is moon, then it becomes a very difficult problem. And it was very difficult to solve. So he asked this question. He has a very different way of thinking, which he proposed. He asked whether our solar system is stable. And it was he who actually gave some kind of this idea about chaos, that he actually predicted that deterministic system. It means this is all you can define very well the equation of motion, but they may exhibit aperiodic or sensitivity to initial condition kind of thing. This kind of systems can exhibit. And then his question was whether solar system is stable or not. And later on in 1950s, like mid of 20th centuries, a lot of work was done, particularly on Hamiltonian chaos. Like today, I'm going to talk about dissipative chaos. All this biological system chaos was dissipative. And I think tomorrow, day after tomorrow, Santhanam is going to talk. He will talk about, I guess he will talk about Hamiltonian chaos. So Kolmogorov, Arnold, Moser, a lot of mathematicians and physicists, they started working on various theorems and about chaos thing. So all these theoretical things were there. but it was not until 1950s, like at that time itself, the computer came into the picture, and people can do this calculations on computer, and that was the key point in in this bloom of chaos. And I'm just quoting here the apparently the first experiment when people observed chaos, when someone, because earlier it was all in theory, but this observation of chaos was first possible, and that was in this experiment by Edward Lorenz, who was the meteorologist actually. So he was trying to give a very simplified model of atmospheric convection using all this fluid dynamics Navier-Stokes equation. And so for the weather, because he wanted to forecast weather, we know weather forecasting is still difficult problem. So he wanted to forecast weather, and he just gave some few very simple equations based on this Navier-Stokes equation. And then he saw chaos, and how he saw chaos, that was actually just by chance, I would say. So advent of computer in mid-20s. So what he did in 1960s, this Lorenz, he made a very simplified dynamical model. I will tell you, it was the three very simple equations he gave based on the Navier-Stokes equation. And what he taught, that if I give you the present temperature, pressure, humidity, and wind speed, etc., it should tell me that what will happen at future time. That is the entire weather forecasting is about. So he was doing this small experiment in this computer. Actually, 1950s, our computer looked like that. So I got this picture from also internet, that how our computer looked like in 1960s. So one day he decided, okay, so his simulation was running, and he was printing his result in a paper, and computer was simulating the things until the 6th decimal, but when it was printing, it was only printing until the third decimal point. So after 3 decimal, it was not printing anything, or it was printing 0. So what he did when he took the paper from the midday of the previous day simulation, and he thought, okay, let me not start the simulation, I take the data from the middle, okay, and let me feed it and again evolve, okay. So what he did inadvertently, that 6 decimal thing, he rounded off to 3 decimal. So you can see that your error is lying still at the 10 to the minus 3 position, okay. So your error is 0.0001 of the order, okay. So with this error, he again put back this initial condition in his model, and he started again calculating with the computers, and the results was not matching at all. Actually, the results which he saw, that was shocking, kept on repeating from the intermediate value, and results were never matching, even not matching in the close vicinity. The results were very different. So just he made the error in the third, after the 3 decimals, the 4th decimal, he made some error, because his calculation was for 6 decimal, but since he put only the accuracy until the 3 decimal, and that error, such a small tiny error, was giving him completely different result. So what that's Lorenz noted, that you can see this is the actually from his own this time series. So you can see his time series were never matching. So after a certain time, they were diverging. Okay, they kept on diverging, and they had no similarities actually. And first he thought that his computer was malfunctioning, and then he realized that this is the kind of system where a little change in the initial condition may lead to the completely different dynamics. And that was the first observation of chaos in real system. So chaos is sensitivity to initial condition, that we know, and this is the reference for the original paper. And later on, first he published in the atmospheric journal, no one paid attention, and later on, then he started publishing in other journals, and it came into the picture. So this is the reason that why long range forecasting of weather is not possible, because of the intrinsic, the system is chaotic. Intrinsically, the system is chaotic. So any error, if it is made in the initial condition, the prediction would be completely different. So, and this is a very simplified model. You can see 3 variables. So chaos does not mean we need a large system or many variables. Even I will show you a beautiful example that only 1-dimensional system can show chaos. So this is simple 3-dimensional, simple exact 3-dimensional coupled differential equation. And depending upon the parameters, which you don't need to really worry about, it can show from the fixed point to the chaotic attractor, which is mentioned here. You can see that it spans the entire phase space. Actually, this is the point, and the essence of this, that if you made a small error in the initial condition, you may get completely different dynamics. Okay, And this is that beautiful butterfly thing, which also Dr. Ian McCallum was talking about. And this butterfly is just simple metaphorical example given by Edward to show the sensitivity to initial condition. And what does he say? That flapping of wings of a butterfly weeks earlier, just a small tiny disturbance in the atmosphere, because butterfly has flapped the wings, but it may lead to very different path tornado may take. So formation and path taken by the tornado may be completely different just because a small perturbation somewhere in the system. So that is the idea which was there. And here I am just putting one very beautiful mathematical definition. After that, I am not going to use much mathematics. So this is a mathematical definition which I liked very much. And this is taken from this book, Robert Devani. And I request anyone who has a bit of mathematical background can understand. It's a very beautiful book. And these definitions, which I have the three properties of chaotic system, which I have written, that sensitive to initial conditions, okay, which is like a small perturbation can give very large, like the trajectories will diverge, okay. And the second is topologically transitivity, which is here, which I've tried to describe in the picture, but I'm not going to pay much time here, but I am going to use all these words here and there, and that's why I thought, let me introduce. And periodic orbits are dense, okay. They are all unstable, but they are dense. Like you can think something like if you have 0 to 1 scale, and then if you ask the rational number, they are dense, okay. Rational numbers between 0 to 1, they are dense. So here, suppose periodic orbits are rational numbers, but they are having measure 0. So if you measure them, they are measure 0, because anytime if you pick up any point between 0 to 1, you will end up with the irrational numbers. So periodic orbits are dense, but with the measure 0. So this is the very nice definition. And here also some very nice book, which I would like to suggest. This is the Chaos and Nonlinear Dynamics book by Hilborn. That is for very basic people who doesn't know any mathematics. This is for introduction for actually engineers and biologists, for everyone. And for very serious reader, I would like to also suggest the Sichenberg and Leiberman book on regular and chaotic dynamics. So with that, let me come to this very simple population dynamics model, which becomes so popular because you can see here, I like to draw your attention that it is such a simple model. You can see that variable x, this is only one variable x, which is there. So only one variable, which is here. And I will introduce all this bifurcation, and then only you will be able to appreciate the chaos in biology. If I just start talking about the chaos in biological system, you may not be able to appreciate. So because of that, I have chosen this very simple model, which is here. So you can see the value of x at n+1 time that depends upon its own value at xn time, okay, and 1 minus xn. Very simple model. So you can see this model was given by Robert May in 1976 in Nature, where he was again a mathematical biologist, and he gave very simple model for this population growth. So you see the population will be growing with proportional to r xn, but it will also so there is a this death rate, because people will die, and this death rate is given by minus of r xn x square. So first part is the growth, because reproduction, and the second part with the death or competition for the available resources. So very simple model he gave, okay. And this very simple model, now there's only one parameter you can see. There's only one parameter which is there, and which is r, okay. And with this one parameter, I will also be taking the questions. Please keep on writing down there. So with one parameter r, I can, he has shown that this model shows so many different behaviors starting from regular to chaotic, okay. So let me show you now. So if you take r less than 1, no matter you start from there, where. So if you start away from 0 to 1, you can very well see, you can take a pen and paper, and you can see that you will always go to the minus infinity. So you cannot go beyond 0 to 1. So xn is confined between 0 to 1. So any initial condition you start with. So here you can see this green dot that is started from 0.18 approximately. After few iteration, now you can see it is going to 0. Again, 0.75. After few iteration, the population gets extinct for r less than 1. And there's also a very tedious proof of this kind of gloomy behavior. But that's there. All this information, if you have Strogat's book, a very popular book by on regular and chaotic dynamics by Strogat, who is a very nice author also. So you may try to look into that. So you can see that from wherever you start with, population will always extend, okay, for r less than 1. Okay, now let's see. So r I am keep on now increasing. Okay, so let's see what happens when I am increasing r. So this is Strogat's book reference. Now suppose I take r, I start increasing the r from 1, and then what he observed that you start increasing r from 1 to 3. From wherever you start with, the population will go to the fixed point, and you can always calculate theoretically also this fixed point. I am just showing it for the visual appreciation, that you can see from wherever you start with, it will always go to the fixed point, and this fixed point is stable. So you have this fixed point and which are stable. So you can always calculate the fixed point from this equation. So from wherever you start with, you will always get a fixed point, nothing really interesting. Now you keep on increasing r. Yesterday also there was very nice talk by Professor Sudeshna Sinha on chaos, and she was also talking about the this logistic map perhaps. So now one can see that as r keep on increasing, now you can see the behavior is changing. Now you are getting the periodic orbit. So one parameter, this equation, very simple equation, one parameter equation, but now you can see that it is showing the periodic orbits. Okay, and then period is increasing. Still it remains periodic. Period is increasing, but it's still periodic. Now keep on increasing r, then period will keep on increasing 3, 4, 5. Now how long this period can go? Period will keep on increasing, and so our utter surprise, like from r is equal to 3 to 4, period will keep on increasing, and it just goes to infinity, which is here. So you can see it becomes completely aperiodic. There's no periodicity here. So this is one thing, it is not periodic, but the most important thing is a sensitive to initial condition. What does it mean? Okay, I'll show you here in the next slide. So I have started with, very close to 0.95, okay? So I have taken two initial conditions, and they are so close that you cannot see the difference in the beginning. They are mapping on one another. So I have taken two initial conditions, which is very close to each other. So in the beginning, you can see that if you can see, follow my cursor, in the beginning, they are only red lines. So I have plotted this x as a function of time, and two initial conditions which are very close to each other. So you can see this only red curve. So they are almost matching with each other. And after a certain time, they start going away from each other. You see very small difference in the initial condition, which is very, very small. But after a certain time, you can see that two trajectories are very different. So this is the sensitivity to initial condition. Aperiodicity, or I can say periodic orbits are dense here for logistic map. You have periodic orbits of all period, but all periods are stable. All periodic orbits are unstable, and that leads to chaos. Denseness of periodic orbits, but all are unstable. So trajectory is so this leads to the sensitivity to initial condition, transitivity and periodicity. So you can see that they are completely diverging, and that is the population model, which was become very popular. And I have just shown here different dynamics shown by the same logistic map depending upon the value of r. And now let me take up a few questions which are there before. How to know how chaotic a system is? So I will tell this thing, this is Latour experiment. I think so. This question I will take up later. And this is very beautiful bifurcation diagram. So with r versus x, and you can see in the beginning, you have, as you are increasing r, you have only fixed point, and there's a bifurcation, period 2, period 4, and this is universality class, a lot of rich mathematics and physics which exist here, which I am not going to describe, but you can see that there's a period doubling, and period doubling route to chaos. And later on, you can see the phase space is completely filled. Now, let me come to this promise thing, which is this chaos in biological systems, okay? So I have shown that you have aperiodicity, okay, and sensitive to initial condition, because aperiodic systems may not be chaotic, they may be random, but it's a sensitive to initial condition, which is the key factor here. And so you have this Fusco-Nagmo model, which was given to model this neural firing, actually. So in 1952, this Hudson and Huxley, two scientists, they tried to give a model which can give you the movement of ions in nerve cell during the action potential. Okay, So, and this model which they gave, that become very popular because it was producing behavior of cells like firing and activation, inactivation, rusting properties, bistability at very great accuracy. And then he used all these concepts of Poincare plot, which I showed in the first slide, that Poincare has a lot of contribution in the chaos development. So this model became very popular, this kind of model, because it showed, and this model shows non-periodic and chaotic behavior. So right now, still I am talking about model. At the end of my talk, I will show some data from real world system where this chaos in the brain was shown to exist. So this model which he introduced, that shows all the behavior and captured aperiodicity, but this model shows chaos, okay? And this is the phase space plot, which I am skipping right now. And this is very simplified. So Hutchinson-Huxley model was very complicated. Later on, a small, a simplified version of Hutchinson-Huxley model came into the picture, which has only, you can see, only two variables, V and W. V is the membrane potential and W is the recovery rate. And this simple two-dimensional model, depending upon this parameter A, it may show periodic to the chaotic behavior. This is a phase space, V and T. You can see that this is the phase space. It is like ergodicity in the phase space. So, and here you can see completely very aperiodic kind of behavior depicted by this model. And it has huge application, like last 20, 30 years has seen a huge, like enormous number of papers on this coupled in Fusco-Nagmo oscillator model, because when you couple them on the network, one can try to understand very different type of phenomena like epileptic seizure, etc., can be modeled using this coupled Fusco-Nagmo oscillators on the brain. So this model has got tremendous attention from people working in neurosciences and from physicists because of it can give you very nice kind of synchronization and etc. behavior, but this model itself is chaotic. And then I have another model which I have written here, which is very nice. This is Mackay-Glass model, which is the delay differential equation. And originally he gave this model for to model psychological disease, psychological disorder as dynamical disease. Okay, and I will take you one example, which was for the blood cancer, for formation of the blood cells for the leukemia patient. That is there in the next slide. But this model, you can see it's a very simple model. So here PT is cellular production, okay, of blood cell. And this tau here is the parameter. Tau is the time delay. So time delay can happen because, you know, there is a finite speed of transformation of information. Okay, correct. It can never exceed from the speed of light. So you have always some delay. Now the thing is that anything, like suppose you see something and you react. So there is a delay. So you see something, your visual cortex, and it says the signal to the motor cortex, and then you react. So there is always some delay. The crucial point here is that whether that delay matters or not, but there is always some delay. Whatever you do, some action. So you take shower, and then suddenly the warm water starts coming when you put the knob. So your body feels the water and then you sense and then react. So that delay is very small, because if that delay is very large, you will burn before you will realize that water is too hot. So delay is always there in all the system. Now the thing is that whether the delay matters or not, that is the question one can ask for. And here for this equation, Mackay-Glass equation, which he tried to give for the some psychological disorder, their delay matters. So PT here is the cellular production, and tau is the time delay between production of the cells and release of the mature cells into the blood. Okay, and eta is the death rate of the cells that die. So this is the death rate. So this again, this is a very simple one-dimensional model. Of course, this is with delay. So it is, you can say, tau dimensional differential equation. And this also, like this model was later was shown for this blood forming process in blood count for the normal individual and the first stage of leukemia patient. And one can see that this kind of chaotic behavior, which I am showing in this slide, you see that depending upon the value of delay, this is only one parameter delay, it can go from periodic to this kind of irregular or chaotic behavior as you are increasing this delay. So now here there is one small simulation which is there as tau is increasing, this is a phase diagram, which is plotted here, PT versus PT minus tau. And one can see that the dynamics is becoming more complex. You can see in the beginning, it was only one limit cycle. Now it is occupying the phase space a lot. And now you can see that dynamics is becoming more complicated. And this is again the same, like your logistic map, the kind of bifurcation diagram was also there for Mackey-Glass model for blood forming process. So you have this count of blood cell that is also periodic, and then you can see it is going to the chaos. And now this is the also answer to the question, and also like how to measure chaos. How do we know whether it's a chaos or not? Because irregularity, maybe you can have long periodicity. So what is a measure of chaos? How would you know that a system has chaos or not? Okay, and there is a measure of chaos, which is the Lyapunov exponent, and the Lyapunov exponent is nothing but it calculates this divergence of the nearby trajectory. I'm not going to explain this thing, but this is, I am just telling that you have this measure of chaos given by the Lyapunov exponent. If the system has Lyapunov exponent which is positive, it means it's chaotic, and if it is negative, Lyapunov exponent is negative, then system is periodic. It may be possible that period is very high. So if you have time series of 100 steps, your period may be 1000. So you may not see this again recurrence, but the system is regular. But if lambda is positive, then your system is chaotic, and lambda is 0, Lyapunov exponent is 0. This is the like known as quasi periodicity kind of thing. So now here I have just written that if lambda less than 0, then you get fixed point kind of thing. If lambda is greater than 0, then you can get this kind of chaos. And if lambda is 0, for example, largest eigenvalue, largest Lyapunov exponent, then you have quasi-periodic. So you can see it's a near periodic. You can see it is never reaching to the period. It is exactly never, but it is close to periodic kind of thing. And this kind of all this behavior are seen very well in the biological system, and many systems like lasers and maybe other system, electronic circuits. So many systems show this kind of periodic or chaotic behavior. And now I have one more example, which is of Rossler oscillator. Again, Rossler oscillator is also used for the biological system. Here you can see that nonlinearity. So there's a very important point here. The any system which show chaos has to be nonlinear. Linear system cannot show chaos. And reverse is not true. It's not like all nonlinear systems show chaos, but for chaos, this is a necessary condition that your system should be nonlinear. So here you can see first two equation is completely linear. Well, in the third equation, you have Z, which is coupled with X, and it is making it nonlinear. Okay. And this system also, you can see this is the Rossler oscillator. So you can see there's no periodicity, etc. It's a very dense kind of rich behavior. And Rossler system was also used to model chemical kinetics, and it has a lot of applications in the gene regulatory network and in the chaos control. Like in biology, there's one example here, which is also supplied by so there's one person in my lab, one master student, Nikhil, who is working on Rossler oscillator, and he digged out all these examples of Rossler oscillator, and he found that Rossler oscillators are used to model chaos control. And in fact, this paper, which is written here, this Rossler system as a model of chronotherapy, they have used Rossler oscillator system to control this sleep pattern. Like chronotherapy is the sleep pattern. One try to regulate the sleep pattern, and that is used for that. And with this, now I have some real examples. Like this is from the data that normal sinus rhythm time series. One can see it is very irregular, and in fact, people have shown by calculating the Lyapunov exponent that they are chaotic. So here Lyapunov exponent comes into picture, that by calculating the Lyapunov exponent, they have shown that this kind of time series are chaotic. Now here heart rate signals becomes more periodic. So this is for yoga. So as one does yoga, and there's two examples which people have done in some Chinese type of yoga and Indian, and the simple yoga and Chinese some yoga, and they have found that heart rate signals become more periodic during this process. So in the beginning, before meditation, it was more chaotic, more irregular, and after that, you can see this phase space has shrinked. It has become more chaotic. Similarly here, before meditation, it was more chaotic, and after the meditation, you can see this phase space has shrunk down. So, and then mitochondrial chaotic dynamics, so that is also emphasized that in mitochondria, under oxidative stress resulting from the interplay between antioxidant and superoxide generation in respiratory chain, mitochondrial fluctuation can exhibit chaotic dynamics. And here, in fact, they have calculated also the Lyapunov exponent. And using the Lyapunov exponent, they have shown that it can be regular or chaotic. This is like how to construct, how to calculate the Lyapunov exponent from the time series. So there's a very nice book for the very practical application by Holger Kanj, nonlinear time series analysis, where writers have given a lot of different methods to construct or to know the Lyapunov exponent from the time series. Because if you know the dynamic model, then of course you can calculate everything. But if we are giving the time series, then how to calculate the Lyapunov exponent? I think there is some question. Let me also keep on taking. So what do stable and unstable periodic orbits actually mean? So I can give you a very simple example. Suppose you have a bucket, simple bucket, okay? And you put a ball on the bottom of this bucket, okay? And then you give a small perturbation in both the direction. Along the wall of this bucket, you give the small perturbation. What will happen? That ball will come down, okay? So this is a stable fixed point of the bucket, okay? Now you make the bucket reverse, okay? You make it like this, okay? Now on the tip, you put this ball, okay? So this is again a fixed point, okay? But this fixed point is unstable. So if you are not giving the perturbation, it will be staying here forever. So, okay, this is a fixed point. But as soon as you give a small perturbation, it will fall down, slide down. So that fixed point is unstable. So this is one of the example which I have given you to tell that periodic orbits. It means if you are in the periodic orbit, you will be there forever in this periodic orbit. But if you give it a small perturbation, then exponentially diverging, it means you will never ever come back to the periodic orbit for chaotic system. So that is meaning of the stability and instability. So for chaos, you have periodic orbits of all period, and that's something very counterintuitive because you see completely irregular behavior, but you have periodic orbit of all periods, including fixed point, like in the logistic map, which I have presented to you. But all periodic orbit are unstable. So unless you start exactly from that periodic orbit, you will never be actually witnessing that, okay? So that is meaning of, so you have entire technique to do this stability analysis actually with the Taylor expansion and everything, entire technique which are there. So this is answer to Kinzel's question. And now there's a question that can we fit experimental noise into a chaotic system? I don't know if I understand this question, but noise is not chaos. You know, noise is noise. Chaotic system is deterministic. This is the first thing. If you know exact initial condition, you'll be able to tell exactly where it will go. So chaotic system has this determinism, which is it's a basic thing. It's unpredictability because it's our inability to characterize the initial conditions to entire accuracy. So noise is different. I would not say that. And now the question, Garvit is written, how do we know that noise is not due to chaos? So you see, a system is chaotic, and so okay, so let me try to understand or try to, so a system is chaotic and it will give you some chaotic behavior. So yes, it may be possible that the behavior which you're seeing, that is chaos, not noise. Then you have to take back this words. The system is chaotic, you're getting chaotic dynamics, okay? And then chaotic dynamics, you should be able to reconstruct this kind of phase space. Now you see, I have here this actually slide, which is, so if you're dynamics, so on left hand side, you can see the real dynamics. So now whether it's a noise or chaos, you should be able to reconstruct the phase diagram using so many known techniques actually. So this is one answer which I can give to your question, but this is the entire literature which shows that distinction between the noisy time series and chaotic time series. So this is very involved, but if you have chaos, then you get chaotic time series, not noisy. And chaos means you can apply entire entire chaos theory, entire literature, like generated by or proved by all this mathematician, physicists on those kind of time series. But noisy time series will require different kind of treatment. Okay, so now with that, actually, I think I was already to the end of my talk. Actually, I would like to acknowledge this my lab. Actually, this is because of them only this talk was possible, and whatever I am doing also, this is just possible because of the lab. And also the funding agencies. This is just a courtesy thing to thank the funding agency, and thank you all for your kind attention. And please, any questions, discussion, please, you can unmute and you can ask. Either write down in the chat box or unmute and ask. Any question, any elementary, whatever. Please. Yes, Srirang, please.
It was really good, but I had a doubt regarding the
Yes, please.
Lyapunov exponent.
Yes.
What you said when the exponent was 0, it was quasi-periodic. But what exactly does quasi-periodic mean, and why is it exactly on the boundary at 0 between chaotic and?
So this is just simple one example point of view I have written here. So quasi-periodic means it is not periodic, it is not chaotic. It is just, you can say it is, or maybe you can say that periodic orbit, this period is irrational perhaps. Then you will have limit cycle, but it will never come to the exactly at the same point. Suppose if your period is irrational number, not a rational number, then you will still you'll keep on, if you have phase space, you'll keep on rotating there, but you will never come to the exact the same point, but that becomes ergodic. But quasi-periodic means it is not regular, but it still just not chaotic. And lambda is equal to 0. Actually, you never find actually in real world system lambda is equal to 0. You always find either bit positive. Even 0.001 lambda is also makes the system chaotic. So this is first just for the theoretical completeness. I have shown this thing, this kind of very clear example. But in real world system, you don't see this kind of example. That it is just for the picture visualization.
Thank you, ma'am.
So like,
yes, please.
If we superpose two waves, like whose time periods, the ratio of the time periods is not a rational number, then do we get a quasi-periodic orbit?
No, actually, no, that example was not correct, irrational one, because that is ergodic. So that is not quasi-periodic. So again, please ask your question. If you superimpose two periods, correct?
Yeah. And like if the time periods, the ratio of the time periods is not rational.
Again, I told that rational thing was for different one. Yes, because that becomes, because you have entire phase space that gets filled. So that becomes ergodic there in that limit cycle. But quasi-periodic is just if lambda is equal to 0, neither is periodic nor it is chaotic. It is intermediate of that, and this is known as quasi-periodic. So you have the dynamics in higher dimension that will lie in the torus. So suppose if you have lambda largest Lyapunov exponent is 0, is less than 0, then you have a stable fixed point. And if it is the first one is 0 and all other is negative, then you have limit cycle, which is periodic. Now, if you have more than one, which is 0, so you have torus. So you can think that orbit is lying on the torus. So this is the higher dimensional object, and orbit is lying there. And then as soon as largest one becomes greater than 0, then you have a strains attractor. So it is like tori breaking, which is the entire Kolmogorov-Arnold-Moser theorem, which is there, that tori gets broken, and then it becomes the completely chaotic. So that's how yeah. So now there is a question in chaotic system: is there a minimum amount of small perturbation that is required to change the system, or does every small? Okay, so that is, I have to go back to that example which I have written. Actually, let me explain with that mathematical example. So you are right, any small perturbation, that is true for any small perturbation, however small the perturbation is. Okay, it should not matter actually, however small the perturbation is. And then mathematically, let me very precise this thing mathematically. So when I say this periodic, this sensitivity to initial condition, what does it mean? Suppose is x and y are neighboring points. So x lies very close to y, very close. Doesn't matter that it can be very small. So So if the small vicinity of x, n, and y lies in n, and n can be very small, but there will exist some iteration n, which will bring them far apart, where delta can be any positive number, any large number. So it does not matter however small it is. If you iterate for sufficiently long time, it will fill up the entire phase space. So they will be far apart, they will visit the entire phase space. So they can be anywhere after sufficiently large time. Okay, so it doesn't depend. So is there no minimum amount of small perturbation? Any small, even I can show you with a shift map. There is a very popular example of shift map where each time you shift only one decimal point. So any error which is there into 10 to the power minus 16 minus 32 decimal, just in 32 shift operation, it will become the most significant point. So in this logic gates, when you have this least significant number, most significant number, when you convert into decimal into binary, then the least significant number, suppose lying something at 10 to the power minus 32, after 32 shift operation, it will become the most significant. So even the question which you have written 10 to the power, no, even though it will have any small perturbation, the thing is that time taken would be large. Okay, so if perturbation is very small, then it will have large time, but large time does not mean that you have to really wait for a very long time. Like shift operation, I'm telling you, least significant number will become the most significant number in just few iterations. So you can have even small perturbation in smaller time. Suppose now it depends upon the Lyapunov exponent. So if Lyapunov exponent is very small, then small perturbation will take very large time to diverge. But if Lyapunov exponent is very high, then you can see exponential divergence. So nearby trajectory, they exponentially diverge. So you can just see the exponential divergence things is there. So chaos is basically like anti-convergence. Okay, so that's why I have given this example, this pure proper definition of mathematical definition of chaos. So any dynamical system which has sensitivity to initial condition, okay, which is given by this, and this is F is topologically transitivity. Topological transitivity means if you take two set which is there in F, U and V. So after certain iteration on U, you will have they will be non-empty. It means they will overlap each other. So you see, you're starting from U and there is some set V in the phase space. Suppose there's a small region in the phase space, small region which is denoted by here U, and a small region which is denoted by V, and then you iterate it for k time period, and then you can see there is an intersection. So this is a transitivity. And third one, periodic orbits are dense. So periodic points are dense. Okay, so any of these two implies third. So that is also the thing, but you have the proper definition of chaotic system. So not just anti-convergence. So no, that I would not say, but exponential divergence of nearby trajectory. Okay, but it doesn't mean that they will keep on, like I give the example of 0 to 1, this logistic map. So trajectory was always between 0 to 1. Okay, so this is like exponential growth and folding. So there are many things are like Baker's map is there. Baker's map means like you take something, you stretch it and then fold it, stretch it and fold it. So exponentially divergence, which is there for the local level. Local level, it's exponentially divergence. So I would not say just anti-convergence, but nearby trajectory, they diverge exponentially.
So ma'am, can we say that chaos is known unpredictability? Like we know that it is going to be unpredictable, but we do not know the outcome.
So chaos is unpredictable means, suppose if I give you some initial, you have made one model, okay, and I tell you, okay, with this model, I give you this, right now I am observing this, you feed up this model and tell me what will happen tomorrow, okay. And now your computer has some rounding off. It does this rounding off maybe at 10 to the power minus 32, 10 to the power minus 64. So you have some rounding off somewhere, correct? So even in that small round off, next day you may get completely different result. Now you perform the experiment again. Again, you will get completely different result. This is the point. This is the unpredictability. So you have the rules. With these rules only you are evolving. You are not probabilistically evolving. So you have definite rule. With definite rule, you are evolving the system. But because there is some small error in the initial condition which you have fed into the computer, after 10 days, you will have completely different result. That is the unpredictability, which I would like to emphasize here, because we cannot give the exact initial condition. If we can give exact initial condition until the infinite order, then it will exactly reproduce the same thing each time. There's no unpredictability. So it's a pure deterministic thing. So is there any way to element round off? Yes, actually in computer, that's why it's very difficult to witness chaos. Sometimes you will find that you give the initial condition, always it is rounding off at one place, and each time you are getting the same thing. So in computer, like logistic map, you run in the computer, and you can define this floating and all these things. And many times you will find that you may not get chaos. So you don't have to give very good precise one. You can give it the less precise initial condition. Maybe actually this graph, the logistic map graph, which I had shown you, which let me go back to this bifurcation diagram of logistic map. And this was my first, that time I was doing my PhD. And we had this, I still remember 32 MB computer, RAM space was 32 MB, which you guys even don't know now. 32 MB, and I was sitting in a physical research laboratory in my lab in the late night, and this was a new topic at that time, all this chaos and all this logistic map on network. So that was my PhD topic at that time. And I was sitting late in the night, and that was my first code in life, and I wrote down this logistic map code, and computer was very slow. I was using GNU plot, which is still all of you are using. And then I had data which computer has to load. This GNU plot has to load and has to plot. So x-axis was R and y-axis was X. Okay. And then it started plotting like this. It started from here, left-hand side. And then I was seeing that plot was coming. And then I was seeing this bifurcation and this bifurcation. And that was really the most beautiful picture for my PhD, that I was seeing this thing happening, that bifurcation very slowly. And then I saw this entire chaos. So you can do all this thing in your computer, and also you can take care of this rounding off in computer. What is the reason for getting a small windows of non-chaos? Actually, this is this bifurcation diagram. It's a very rich. Why it got like May published this paper in Nature, and he is one of the well-known scientists, mathematical biologists, and this is still like people in entire world. You can find so many papers coming on logistic map. It's still like you see 1974 he published this paper, and very nice, beautiful paper. PRL papers are coming, which is on the logistic map. You see, this is period doubling, and this is the period three. So you have chaos, and yesterday Sudeshna Sinha was also actually talking about the same thing. You have chaos, disorder, and then some regularity, some order intermediate. And there is you have periodic window. Here you have periodic window of period 3. And actually, period 3 indicates chaos. So if you have periodic orbit of period 3, if you witness, it means eventually you will get chaos. So this is very beautiful. Actually, you get all this kind of in between, and you have this Feigenbaum universality, which actually describe this kind of behavior. So which says that at what value of R you will get a bifurcation actually. So all this picture has very rich in the, so what is the reason of getting small windows of non-chaos in the plot? So system becomes periodic, so order and chaos, and later on it becomes completely chaotic. It's just the property of that logistic map, that you in between for those R value, the periodic orbits become stable, and you can do the entire stability analysis to show actually that at what value of R periodic orbits will become stable. So you have this entire thing. So you can do analytically, you can show that when periodic orbits will become stable. And please show the slide with a list of books. Okay, I will show that. But Garvit, did I answer your question?
Yes, ma'am.
Okay. And I think I will keep on showing many books, but I don't know that this slide. One slide I talked about Lichtenberg and Lieberman. I will share the slides, so don't worry. The slides will be, I have already shared with IISER Pune, and they will tell you. So you will get all the books name which are there. And I think I have still not satisfactory addressed this quasi-periodic thing. I'm thinking perhaps I have so many things. Maybe I'll again try to, please write down to me personally. I'll try to address those things. Anything else? If anyone has any other question or comment or any interesting thing which one wants to discuss.
Not the graph of that that chaos plot. There is a torus, right? So it's a like it's a 3D like it's not a surface thing, right? It's a whole like how to express, like it covers the whole area, right?
Yes, actually, yes, it covers. So here you can see that's why this transitivity. Now you start from any place from the phase space, you will cover the entire phase space. So that is the thing. So anywhere, so this is the attractor. Actually, this is a dissipative system. So you start from somewhere and then you have attractor. Within the attractor, you start from anywhere, you will finally actually visit every place. And that is the meaning of you have this kind of plots, which actually even this plot, if you can see here in the last one. So here phase space, so this is with tau. So you will cover actually entire attractors. So yes, so you are right, actually, it will cover the entire thing. So suppose you have a periodic orbit, so you will go from here to here, here to here. So you have very periodic thing. But if it's chaotic means you will cover the entire circle. Suppose there's circle and then something is moving on the circle. It's a periodic, then you will know that it will come periodic and it will come back here. So one period it goes here and then come here. But it will cover the entire circle or entire phase space. And that is the transitivity which I've shown, that you start from anywhere in the phase space and there will exist a time t that you can go anywhere else in the phase space. You define two small section in the phase space, for example, and you start from this section, you start iterating. And wherever this section is, how tiny this section would be, there would be one time t in such that you will come back. You will be intersection with that space, and that is the chaos, this transitivity thing which I was saying.
So I'm taken.
Yes, please. Yeah.
So I'm taken a little part. Would that not become a Mobius strip?
It will not become what?
Mobius strip, like the Mobius strip also goes from all points.
What's a Mobius strip? Perhaps I don't know. What is Mobius strip?
Well, I don't know properly because I don't have math subjects at the moment. But as far as I remember, I think the Mobius strip is one strip which covers, which does not have a backside and a front side.
I see. I don't know, but yeah, but they are self-similar structure. That is also one can say that chaos, like fractal and all those ideas that all came together. This Mandelbrot fractal thing, that's Cantor set. So you have a lot of things which is common with the fractal or Cantor set, which is there. That's why I suggested this Devani's book, which is very nicely mathematically it is explaining all this thing. And you know why the sensitivity to initial condition or transitivity is there. This is like periodic orbit is dense. That is the very important thing. And I would like to explain just using one example. Suppose you have 0 to 1. If I give you 0 to 1 line, so how many rational numbers are there between 0 to 1? Infinite rational numbers, you see. So this infinite, so that those can be infinite periodic orbits. But if I tell you that you choose any point between 0 to 1, you will not land up into rational number. That you land up with irrational numbers. And irrational numbers are also infinite. But rational number would be measure 0 because you will not land up with rational numbers. Whatever precision you take in that 0 to 1 line, you'll always land up with the irrational number. So you have periodic orbit, which you can see corresponding to rational number. So they are dense, but they are all unstable. And this denseness of the periodic orbit is the key essence of denseness and instability of this periodic orbits are key essence of all this kind of chaotic behavior. Sensitivity to initial condition, all these things come because of this denseness of the periodic orbits.
Understood. Thank you. I think we have one more question.
Yeah. Was the name butterfly effect given because the graph looks like? Yes, actually this is, I have even, I also tried to see actually before I was presenting that why this butterfly name came into the picture, and then Sanket also helped me a lot, who is also doing PhD in my lab. So, so this is actually named by Edward Yacht, and this was a metaphorical example just to show, because it looked like butterfly, you see. Lorentz oscillator, when he plotted this phase diagram into x, y, z coordinates, he just plotted, and then it looked like a butterfly, and then he gave this is a metaphorical example that this is a butterfly and it flaps its wings somewhere and it can divert the path taken by tornado. So you are right, this is This is just a metaphorical example given by Lawrence because this looked like very beautiful butterfly. Yes.
Okay, so do we have any more questions or any comments to share?
And actually, this Tucken's theorem is very useful to build up chaotic kind of phase diagram from the given time series, which I have not given here, but I'd like to just mention here.
Okay, so at this point we'll conclude our discussion. It
And
was a really
I just want to add just one more small thing. Now you take two chaotic map. So let me now add just one more thing to your excitement that why this logistic map is very. So now there's one logistic map. Now you add one more logistic map and couple them. Then what do you expect? So I am increasing the complexity of the system because one thinks that the more complex a system is, more chaotic is, and I'm telling you no, that's not correct. So suppose I have two logistic map and you couple them. What you expect will happen? Suppose you take one logistic map which is chaotic, R is equal to 4, where it shows chaos. You take another logistic map which is R is equal to 4, it shows chaos. Now you make a coupling between them. What do you expect? Because system has become very chaotic, correct? Two chaotic system when you couple. The strange thing is that depending upon this coupling strength, you can get completely regular behavior. So individual, they are chaotic, but because of coupling, so if you make system more complex, does not mean that it becomes more chaotic. So this is the thing which is very counterintuitive for like system need not to be complex in order to be chaotic. Very simple system can show chaos. And if you increase the complexity, does not mean that you are increasing the chaos. Two couple maps, very simple one, couple them. They may show very cute, very simple periodic even the fixed point kind of behavior. Oh, no, it is because chaos and chaos may cancel each other. No, no, actually, no, it may also lead to the hyper chaos. So I am not saying that they will always show. Depending upon the coupling, it may show hyper chaos. Hyper chaos means you have more than one positive Laplace exponent, okay? And it may also not show chaos. So this is only one example I'm trying to emphasize that enhancing complexity does not mean enhancing chaos. It may or it may not. This is the only point I want to convey. So you may also get chaos if you couple two logistic map, but depending upon the coupling strength, you may also get the periodic behavior. So that's it. So that's it from my side now.
Okay, so we'll conclude the session at this point. We are really thankful, ma'am. It was a really wonderful experience to attend this talk, and we know that we had approached you at the very last moment, and it was a very short notice, but you still agreed. So we are very thankful for that. Thank you very much, and thank you everybody for attending the talk today. It was really wonderful to have you here. And we still have events going on. The next event is tomorrow at 6 p.m. That is Professor Santanam's talk on chaos in physics, followed by a live talk, which would be hosted by Professor Sunil Mukhi on Monday at 6 p.m. And wish you all a wonderful National Science Day. Thank you.
Yeah, thank you, Ashmita. And still anyone has any question can write down to mail also to me, and I'd be happy to address that. So see you all, and